I'm James Robinson. You're listening to Multiverses. There's much debate about whether the current dizzying rate of progress with AI can continue. Perhaps the technique of pushing tons of data through neural networks will start to deliver diminishing returns. Perhaps we'll need to encode by hand some symbolic logic into our systems, a return to GoFi or good old-fashioned AI. Or perhaps we'll need to endow AI with sensory capabilities. Perhaps it needs to be embodied before it can truly realize AGI. But I think it is fair to just say that there is agreement among a large part of the AI community, at least, that in principle, AI can tick off all the cognitive capabilities of humans, that it and indeed can surpass them. Our guest this week is Selmer Bringsjord, a professor in cognitive science at RPI in the state of New York, where he's also the director of the Artificial Intelligence and Reasoning Lab. Selmer is a very interesting voice because he doesn't believe that machines are even in principle capable of all the kinds of thinking that humans are capable of. He thinks there are certain forms of problem that are simply off limits to any machine which is operating at or below the Turing limit, i.e. any machine that we can currently conceive of. And yet humans, he argues, are able to deal with those sorts of problems. And he points to problems like our ability to conceive of the infinite. And he points also to things like Gödel's theorem, although his views on that are a little bit more subtle. So this is, I think, really worth listening to, not only for Selmer's, I think, heterodox views, but for the really cogent arguments that he puts forward, because the arguments in themselves are just wonderful as an introduction to problems in the foundations of computer science, to issues of computability. And actually, Selmer calls me out on this quite early in the conversation. I think for many, computability and Turing computability have become synonymous. And Selmer points out that actually what is Turing computable is just a tiny subset of all the things that are computable if we look beyond the Turing limits, if we look to hypercomputation. So it's just a lovely overview of this sadly neglected, I think, field in computer science of things that go beyond the Turing limit. Of course, the reason why that field is neglected is we simply don't know how to make anything that goes beyond the Turing limit. And yet Selmer argues we are somehow able to do it ourselves. So a really interesting conversation, and I hope you enjoy it as much as I did. Hi, Selmer Bringsjord. It's a real pleasure to have you here.
Well, it's quite mutual. Thank you, James. It's a pleasure to be here and looking forward to our conversation.
Thanks. So I think that the early Wittgenstein said something to the effect that the boundary of thought and of language are the same. Those boundaries are one and the same. I think many people would disagree with that, and probably the later Wittgenstein disagreed with that. However, I see a kind of growing trend for people who would say, well, the boundaries of thought and of what is computable are the same in a certain sense. What do you say to that?
I say first that formally speaking, by that I mean generally in terms of mathematics and formal logic, or to use the fancy adjective logico-mathematical. From that perspective, there's something objectionable right off the bat in the question, because computable really, in light of advances on the formal side in computer science, could mean something more than what a Turing machine can compute. So I think we have to be clear that generally speaking, when people assert the view that you are correctly saying is quite popular, if not in the vast majority of people think about such things, it means Turing computable. We have to be clear about that, because the way I use the term computation, and I'm not alone, computation and what's computable uh, could be forms of or include forms of information processing that are beyond what a Turing machine can accomplish. And that's been with us, ironically. This is arguably an indictment of today's educational system in computer science. That's been with us for a long time. That's been with us since the dawn of what we ordinarily think of as computation. Turing came to the United States to study under Alonzo Church, the American, and Church wanted Turing to try to escape the very results that the both of them, negative results, the both of them had produced, which were about the limits of standard or Turing level computation. For Church, it was the lambda calculus. For Turing, it's what we now call a Turing machine. And when I say Turing computable, that means what in principle a Turing machine can do. So they explored that together. I think Turing, it's been reasonably well established. It's not totally uncontroversial. Turing didn't like it particularly. I don't think he was disposed emotionally uh, in favor of the very investigation that he made seminal, if not more than that, inaugural contributions to. But Post also is in the. So these are the three. These are the three people who gave us the first fully mathematically respectable definition of standard computation, right? Um, Post explored computing in his own style beyond what a Turing machine can accomplish. And we have Post's theorem, which is about the very space beyond what a Turing machine can muster. So, to your original question, again, first thing we got to be careful about is the assertion probably is the bounds of thought line up with, maybe they're coextensive, the bounds of what's Turing computable, what a Turing machine and its equivalents can compute.
Mm-hmm.
Right. So, all right, now that we have that, for some anyway, arguably clarified, I would say we already have part of what must be the answer on the part of some people, which is no. So I remember the one and only interaction I had with Marvin Minsky, one of the founders of AI in the modern era, now deceased, one of the so-called 56ers. He, he was doing his usual thing, totally aligned with the identification of uh, what thought is and what Turing computation is. And I remember saying, "Okay, look, fine, that's your view, but we do agree that that means that since all of standard computation above Turing machines and below is based on functions from natural numbers to natural numbers, do we agree that that is an uncountably infinite set? And your view entails that only the tiniest sliver, it would be sort of an infinitesimal number of these functions, would then be computable by uh, the mind, the human mind, or if we say there's nothing beyond it, then a mind. And that seems really, really, really odd to me. Uh, why? Well, how is it that the very minds, and I haven't published this argument, how come then the very minds that are so imprisoned in this sliver of Turing computable functions is able to plumb the depths of the larger space? This mind is able to establish all kinds of interesting results, theorems about the larger space. Doesn't that seem odd? So, it was a brief but violent, intellectually speaking, exchange. And that's sort of the start of my problem. The very moment we clarify what we mean in this assertion, the next thing we have to do is concede, oh my lord, that means I was sort of fast and loose ignoring the space of information processing that in the abstract certainly exists and that which the human mind has plumbed. So that's, to me, suspicious, minimally, right? Then I would say I'll stop at three. This is another one that I really haven't published. Both of these two arise in a long-standing debate with Bill Rappaport, an American computer scientist. Someone's got to tell me when we're going to say it's been long enough that AI has been telling us human mind will be matched, but not today, tomorrow. I mean, we have to have some conversation about that. We can't keep saying it's perpetual. No, that's not how science works. We don't get an infinite amount of time for people to keep saying P is true. In the future, we'll confirm it, and then we keep working and it never gets confirmed. But that's actually what I know it's time is relative in this regard. This is what I've lived through to 65 years of age. So I'm an undergraduate there at the University of Pennsylvania. Uh, in that case, it was cognitive, most aggressively stated, it was cognitive psychology. Okay, what's cognitive psychology? Oh, that's easy, folks. Cognitive psychology is the study of cognition based on the driving assumption that all cognition is Turing level computation. That's our investigations based on that. And that presupposition will eventually mean the success of AI reaching the human level. When? Well, not yet, clearly, but it's coming. And so what? I graduated maybe something like 81 or 82. You know, I, it's the same thing. It's the same thing people are saying now. We have had the pushback from pure deep learning. It's the same exact thing. I think four sort of salient times I've lived through this. This last time was all we need is deep learning. It's all we need. Deep learning, that'll give us deep neural networks. And now we have companies like OpenAI teamed up with Microsoft explicitly calling on the engineers and saying, really precise reasoning in the area of logic and mathematics ain't working so well. Help us out. Do you have any resources outside of artificial neural networks used for the formal learning called deep learning? Yes, we do. And Microsoft has huge resources. And so now if you call up like I do, not GPT 4.0, which Sam Altman said was going to be just truly amazing. Now you call up 01 preview, and it's markedly better. It's not markedly better because they started from scratch and made another deep neural network. It's markedly better because of, and here I echo Stephen Wolfram, although I don't have the business interests, because it calls resources that we have known for a long time are really good at explicit, careful, rigorous reasoning and calculation, where approximation doesn't work so well. So anyway, those be my three replies to your initial query.
So I think I first want to explore the kind of second of those, which is this argument that there are things that we're able to grasp as humans, which provably, in a sense, machines can't grasp. And I want to get a little bit more concrete there. But I think it will be news to many. As you say, there seems to be some sort of lacuna in the education of computer scientists. So it'll be used to many that there is this space beyond the Turing limit, and it's a very large space, as you said in your reply to Minsky or your comment to Minsky.
That's
It's
right.
much larger than the space of things that are Turing computable. So perhaps you could start by talking about what that space is. What are the dragons out there?
Yeah. Well, I guess my favorite entry point to that space, and it really isn't just one neat space. It's depending on how you slice it, it could be an infinite number of spaces, but it's definitely two big ones. The first big one basically says if I give you the logic that Frege, he gets credit, although I believe Leibniz had it before Frege, but whatever. I'm willing to give the scoundrel credit. So if you can express it in first order logic, uh, you only got the for all quantifier, you got the exist quantifier, and then we'll allow you to have properties, but you have to announce your properties in advance: red, greater than, less than. We'll let you have your functions to start with, but we'll restrict those. We'll give you plus, multiplication, etc. Whatever you can describe with the variables that the quantifiers are attached to. So you can say for all x, for all x, where x is a natural number, there's a y that's greater than x. Wonderful. If you give me that, and it's not me, then I can quickly pose the challenge of trying to decide whether two computer programs are equivalent, despite the fact that the code is different. Okay, so this would, by the way, be something that causes immediate paralysis of deep neural networks. I mean, they simply can't do this. They could do this empirically up to a point, but they can't do this for many reasons. So that's an entry point that's not that far above a Turing machine. It's a so-called, the terminology really doesn't matter. It's so-called pi 2 formula. So it says, look, give me any two programs. Do they compute the same function? It's really hard to be a first-rate software developer. You can be a mechanical coder, collect your salary, maybe call upon. You could probably just call upon ChatGPT 3 or something like that. Hey, I need this. I need some code that does this. That this is a rough description of a function. Back it comes, and it might very well work. But there's no way that you can do it. You can solve the problem I'm talking about working that way. And so you alluded to the fact that it's a large space we're talking about here, the so-called arithmetic hierarchy. How large is it? Well, it's infinite. Where is the problem beyond a Turing machine of deciding whether two computer programs compute the same function? Pretty much at the start. Pretty much at the start. So it's not really that hard. But I don't see how you could have a job working in high stakes software development without having to deal with this left and right. How do humans do it? What would the contrarian view be? What would the let's call it the equal boundary or equivalent boundary view that you mentioned, thought computing the same? What would they say? Well, the humans are just getting lucky. They're getting lucky on the job. They, by the way, better really get lucky if they're using something like a large language model to get code that they use, because almost right away they're going to have to decide not only whether that code is correct, and that, by the way, that's Turing uncomputable. Deciding whether an arbitrary computer program at the level of a Turing machine, that's uncomputable. We can't prove that it's correct relative to specifications for what we want. That's uncomputable. So the problems that I mention here too now are examples of what, and look, they're not these are not like alien concepts. These are things that people get paid, in some cases, a heck of a lot of money to figure out in the workforce. And I can assure your audience, they ain't using AI to do it. I DARPA had a program where they threw in the towel and said there aren't enough human beings that can do this kind of stuff. We'll just sort of turn it over to crowdsourcing and hope for the best. It didn't work that well. because you really do need to take the human mind and subject it to training and education, and then it's able to do it. Ironically, Turing and von Neumann were the first folks who did sit down and tackle the problem of proving that a computer program, whether a Turing machine specification or Turing machine description or something else, is correct. And yeah, we don't teach that. We in terms of the lacuna that you alluded to, by the way, educationally. So two things now um, in the conversation that we no longer do. We really don't care anymore if students. We might have a throwaway program verification course at the great universities in the world. The one, or certainly there is one near you, University of Edinburgh. We might have a throwaway class, but it's not a requirement. So you can no longer expect, even at the PhD level in computer science, that the person you ask to prove a given program, even not that complex, correct, can do it, because we don't teach it. And then going back to the earlier subject, we no longer teach the whole spectrum of problems. We might. I know at my university, which I obviously have a soft spot in my heart for, I've been here a long time. We dropped the requirement of studying uncomputability. You only study you only study what algorithms, um, how algorithms should be measured and placed relative to how, say, efficient they are and the size of input, time wise, and so forth. We don't. The minute we have an algorithm, the minute we know we're studying algorithms, then we know we're just studying what's Turing solvable, Turing computable.
Yeah. So when you say that we don't study uncomputability, you mean we don't study non-Turing computability. So could be
That's right.
computable by some other means. I want to
Exactly.
really just
Yeah, that's an important point, because again, implicitly what's meant by uncomputability, and I did it myself, is it's the study of that which is uncomputable by Turing machines, because there's a lot of other stuff that is computable in the extended sense.
yeah. I mean, we should say there's sort of good practical reasons for why there's such a focus on the Turing machine. It's because we don't know how to build anything that we can use that goes beyond the Turing limit. Um, and I think that will surprise some people, because what you seem to be suggesting is, well, actually, we can't build something, but we have something that seems to be doing this or capable of doing this, and it's us. And here's an example, and I think I want to make sure I understand this example of verifying that either a program is doing what you want it to, or that two programs are equivalent. And I can see how those two things are quite related. Um, why why is that something that a Turing machine can't do? I presume that there's a certain class of functions and programs where there's an algorithm that covers it. But why is what is the general problem here? And how how is it that humans seem to be able to get around that? Maybe that's a second question. That's a big one.
Yeah, that's indeed a huge question. Um, I don't know how to efficiently, let alone both efficiently and eloquently, encapsulate uh, that which it is. And again, we're just talking about, to use the broader term once again, information processing consists in what's beyond uh, what a Turing machine can do. And one caveat there: the logic I mentioned, first order logic, in connection with Frege inventing it, etc. Theorems expressed in first order logic are there's no Turing level algorithm for deciding, as you no doubt know, whether a proposed theorem is the theorem or not. However, it is semi decidable, or semi more precisely, Turing decidable. So in that case, there's sort of an answer, which is produced by saying, wait, you're telling me that if I sick a Turing machine on the question, is this statement expressed in first order logic, and let's restrict it to number theory, is this statement a theorem that it's it's going to work for sort of half the problem? Well, which half? It's when it is a theorem, it will find it. Okay, so then wait, so okay, well then what happens in the case where it's not a theorem? Oh, I see. In that case, you might never know as processing continues whether it's going to halt or not. So
Right.
in that case, the answer is it's the halting problem, which in its purest form, for your audience, many will, if not most, will know the halting problem is the problem of having to decide in the arbitrary case whether a computer program halts or not. Helpful, by the way, to have a solution to that in theory if you're a counter fraud company trying to evaluate whether people are submitting programs that are any good or just throwing them in and trying to get the letter grade. But there it seems like okay, we have a toehold because we have the halting problem. However, even there, I think we better be really humble. At least I'm going to be humble. Um, why? One reason is when I prove it for students early on, the halting problem, I actually just, I mean, I'm not a constructivist, so I'm a Platonist in mathematics. I'm using indirect techniques to prove that there can't be such a machine based on contradiction. Uh, that doesn't really help me to explain the essence of why this doesn't work out. All it does is throw this wall, this sort of mysterious wall in front of us. I mean, we can work on it, and we can do better, and hopefully we will in the conversation. But the first problem is that alone is really murky, and then you have um, probably even a more sort of initially murkier result, which is what about stuff at that level of trying to say whether a program, specifically a Turing machine, halts or not? What about something like that where we don't have to use fancy indirect techniques and fancy proof techniques to show? What about something just sort of more direct? Well, the grandfather of that, or the primogenitor of that, is a variant where we're trying to just figure out how many symbols a Turing machine in a agreed upon format after a finite amount of time can just put out on its tape or print, in a printer if we physicalize it a different way, so-called busy beaver function. And that's uncomputable. That's Turing uncomputable. That one, so that seems like, uh-oh, that's also mysterious. We might get a toehold there because we know in that case it has to do, well, shouldn't say that. It begs the question against alternative answers to your very penetrating question. But at least in that case, we know that acceleration, something like acceleration, is going on. So the rate of growth of the function that we're trying to compute by standard means grows so fast that we cannot get a Turing machine. No Turing machine exists to handle that level of acceleration because the so-called productivity of the Turing machine, as it gets larger, the amount of stuff it can print out in the size of
Hmm.
those numbers, those natural numbers, grows faster than any Turing level function. So I guess we could say there looks like it might be acceleration. Um,
Hmm.
People have sort of said that about hypercomputation and stuff, or super Turing computation, that yes, but that's really fishy because you would have to have a machine that can do an infinite amount of work in a finite amount of time. So I'm not going to go that far, but I will say there's got there's something going on here about acceleration and speed. Um, but is it just speed in the sense of what really practically minded people focus on in AI and computing? That's the so-called polynomial hierarchy, where everything is Turing computable, fully Turing computable. Their emphasis is always, well, I need efficiency, so I'm sticking with that stuff. This is different, and this takes us back to Minsky's to my interaction with Minsky. This is different because it's not really how long or how much space is it taking your machine and the size of the input where we know the problem is Turing computable. This is a level of speed that certainly looks like it needs more than a natural number or a rational number for us to even make sense of it. And that's pretty much true. Um,
So kind of
so
uncountable speed.
yes, and we know. So if you wanted to sort of, I'm trying to sort this out in the case of quantum computing now. I think, by the way, that quantum computing, now that it's become uh, doable in machines that some are lucky to have available. We have RPI has, I think, the first university quantum computer, thanks to considerable generosity of billionaire and IBM. You know, we can
Very cool.
start toying around with the physics dimension of this, but mostly for provoking thought about whether it would ever be possible to build such a thing. Um, And the shortcut has always been, or for a long time, has always been in the case of neural networks, to allow real numbers into the game, to allow real
Mm.
numbers as coefficients for the equations that allow us to just express neural networks as sets of equations. Um, you know, I mean, Leibniz and Newton had to appeal to the calculus to get engineering off the ground and make sense of the universe even before we got to relativity, and even before we got to quantum mechanics. It uses the reals. There's some sense in which, if you're a formalist like me, you already have to accept the reals as. I mean, if you're a formalist like me, you have to accept that if you need the differential and integral calculus, if you need analysis to figure out what's going on, even independent of cognition and consciousness in the world, is really odd, because that wouldn't be, that wouldn't be computable, right? So how else do we get out of the paradox of the arrow, uh, and so forth? Well, for me, we use the calculus and say, hey, there's the answer, but we just invoked um, analysis. We invoked the reals, and this is interesting. So if the brain makes use of the reals in any serious way, it's definitely hypercomputing. This is not some insane view. If we already regard the brain, back to your question I'm probing about, well, you can't build the stuff, so what's the essence of it? Um, but just an observation here: if we are already the smartest creatures in the known universe, um, so smart that people who said in 56 or 60 they needed a weekend to work out some particular faculty that humans have and failed miserably. Minsky's in that category. I mean, now we have had this rude awakening through the more than half a century. Well, we're the smartest thing we know about. We can't match it yet. We keep saying, I think it's fideism, but we're going to do it. But it's not an existence proof. It just, but what's special? What's special? Well, something's special. We only have a few possibilities as to what's special. If thought and standard computation are the same, and we're thinking things, if anything, then it just must be that somehow we leverage speed and efficiency space wise to get things done, and we just haven't figured out how to replicate it in AI, but it's all computable. Um, or we can get mystical, okay, um, or such. I don't want to be disrespectful, but we could get mystical and say I have no idea, but it's just an impenetrable mystery. We could say we head in the direction of dualism and say, well, we're accessing resources that are non-physical, so it's just the third, possibility. Or the fourth is to say, Penrose is many others have. Well, there got to be effects in the brain that are just extraordinary,
Mm.
and we harness them, but we don't know what they are, and we do it all unconsciously. So we just got to figure out what it is, but it's not going to be standard computation.
Okay. Yeah. Wow. There's really a lot to unpack here, and I think that was just a great delineation. As you say, I think it's very hard to draw the line of where the Turing limit is and why some things are on one side of it and others are safely within the bounds of what's physically computable, as far as we know what's physically computable. As you say, there might be other forms of physical computation. Probably a good moment to
Right.
remind people, though, that even quantum computers, as we currently know them, the algorithms that we have are not going beyond Turing machines. They're able to do things that a Turing machine, also, yeah, they're
Yes.
able to do things very quickly, much more quicker than a classical algorithm.
Yes.
But they can only
Yes.
solve the same sort of things that classical algorithms can do.
Yes. Well, that's the original, indeed, and that's the original result from Deutsch before. Not that far from my office. I'm in my home, but my office at RPI, long before there was the quantum computer over there, Deutsch had the result that, well, things will be faster, but it's going to be standard computation. Um, yeah, I'm not disagreeing with that, but I would say it's a voyage for me. I'm not a physicist. When you approach traditionally the quantum world as a sort of computational logician or even straight logician, um, you you find alternative ways to try to make sense of Hilbert spaces and stuff, but you really never talk about the physical dimension. So I have never really. I don't know. So I'm learning. I have
Yeah.
a colleague who's teaching me, and I will say this. Um, we agree that usefulness in connection with our quantum computer is only produced when we view everything that happens as being everything meaningful that happens for our uses is in complete conformity with standard digital Turing level computation.
Mm.
But um, while the use of the content and the readout that problems posed to the machine from that mindset are in complete conformity, I I don't know that the physics in its in its side effects or in the phenomena that's not central to what I'm calling the readout. I'm really not so sure. A lot of in my I'm really not sure. I mean, I don't know that the physical processes as side effects are reversible. And I'm trying to wrap my head around that because one of my main attacks on the slogan
Mm.
"cognition is computation" is based on the argument from irreversibility. And Turing machines are fully reversible. They're as a computation, whatever computation they perform is fully reversible. We have these are elementary theorems. So the content that we make use of from quantum computation, and we have defined for us, we've defined a few of those are perfectly well defined and fairly standard. They haven't even been parallelized yet in the world. So we're kind of jumping ahead. It should be interesting. But the processes themselves, I'm really not sure. And so, given my view, and I'm not saying that hypercomputation is happening in a quantum computer. I just, for the record, I'm not saying that. I'm just registering my humility, because my view is that unconscious or non-conscious computation that humans engage in, when they sufficiently tax their minds, is hypercomputational. But it's not conscious symbol manipulation or anything of the sort. And Lord knows it's not hand simulating an algorithm or hand simulating a Turing machine. But I believe it's happening. So I'm just, and also years ago, I had dinner with Roger Penrose. He gave a talk at RPI, and that was really, for me, very, very interesting. I think he messed up a lot. His Gödelian, all the Gödelian stuff was all messed up. But
Maybe
that's
just mention so again,
but not the stuff he talked about at dinner, about that was in the realm of mathematical physics, when he was talking about the connection between physics, including quantum, okay, and the brain and the mind, and sort of speculating. There wasn't anything wrong in what he was saying. And it was really, I thought it initially, this is crazy. And then, now I think people are like, I don't know. I guess he's pretty smart. He did win that Nobel Prize, right? And now you have the people who, I don't agree with them at all, people who are taking his consciousness views very seriously, experimentally and physically, not in connection with the quantum computers. And you may know of some of that work. Sorry to interrupt you there.
No, I was just saying. I think I'm going to do a terrible job at praising Penrose's Gödelian argument, but you can tell me how to better put it. But something like the human mind, is not. It's going beyond the Turing computer again, and the reason is it can perceive things like that are non-computable to be true, and one of those would be the sort of classic Gödelian: if this statement is true, you can't prove it. And we can sort of easily say, oh, well, that's got to be true, even though I can't prove it. Because if it's false, then you could prove it, and then it wouldn't be true. So, that's an attractive argument. It would be great if that would work. I want to backtrack though a little bit to, well, firstly, I do want to say one thing about quantum mechanics, because I do think views differ on this. My view, just for the record, is that unitary quantum mechanics, those equations are all you need. You don't need any collapse of the wave function. So that's why this podcast is called Multiverses.
Yes.
And if you believe that, then everything's reversible, and you get an arrow of time from essentially the universe starting in some special state, or at least one end of the universe, one end of time, being rather unusual, and then everything kind of spreading out from there. But at the micro level, at the and indeed at the level of the universal wave function, everything's reversible. Now, what I wanted to get back to though was just this idea, this delineation of what is not possible in terms of Turing machines' computability. They all seem to revolve around some kind of infinity or circularity, which leads to an infinity, or regressive or of some kind. In, for example, the Gödelian case, there is this circularity which has this whiff of the infinite, I suppose, there. And you mentioned that some of these problems would be solvable if the Turing machine could run infinitely fast, or even I think there's a kind of this concept of a Zeus machine where if the tape that the Turing machine was reading in, if that movement just sped up every time, if it halved, let's say, every time, it would be able to do things like enumerate all of the reals in a finite time, or at least all of the integers. Sorry. Now, that's, and that gives again an idea of why some of this stuff is just not physical, at least classically. But I think what you're hinting at is that maybe a quantum computer, even though we're only able to get out finite results, and so far we don't have any kind of conception of quantum computing which would take us beyond the Turing limit, it seems behind the scenes to somehow make use of infinite possibilities. There are these infinity of states that it can sort of survey over, and perhaps in a similar way, perhaps in a different way, that's the key to what might make humans different to anything that's Turing, any kind of machine or that is a Turing machine or equivalent.
It's certainly inspiring to. That's all that's happened in my case at this point. I was not prepared for how inspiring looking carefully at what's happening with guidance in this quantum computer, independent of my harnessing it for standard problems. It is. I'm as you said, I'm in no way saying it's hypercomputational, but it's very inspiring.
Mm-hmm.
It's not the way people like me think at all.
Yeah.
It's just I mean, see, the problem is your question is what is the essence of what's beyond, is the Turing limit, let's say, is so it's so profound, it's so deep. Um, it's the answer to the question, to return to it from the standpoint of formal logic, is very different than what you describe as a process that's the Weil machines or the Zeus machines. They help us from the procedural perspective. They
Yeah.
help us if we think of computation as a procedure. Okay, no one doing logic from Aristotle to our conversation here in 2024, no one thinking of computation uh, as reasoning in logic or in logics that we have. No one thinks of that procedurally. If they think of it procedurally, it's only because someone pushed them, it could be themselves, to think of mechanizing reasoning over content expressed in a logic. The astounding thing is that Aristotelian logic, so we're talking over 2 millennia. We're talking, this is BC. When we write what Aristotle did down in modern notation, every formula that he has only has one quantifier. Okay, so in the syllogisms, all A's are B's. Let's say all B's are all A's are B's, all B's are C's. Therefore, all A's are C's. That's a valid syllogism. He worked out the validity of that and the lack of validity of all the other permutations, with some allowed as well. So all A's are B's, some B's are C's. Does it follow that some A's are C's, etc.? If you look at the notation to show in a class that here are your three formulas for a syllogism from Aristotle, and you say, can a machine answer the query as to whether the third one does logically follow from the first two? Oh yeah, absolutely. Didn't quite have that in 1956, but close. We had it easily in the 60s, and we had it quickly. All right, okay. What if I just add another quantifier to allowable anyway to each formula, and allow you a few more properties. He only had unary properties, like is red is a unary property. There's one placeholder. Suppose we let that be 3, like X is between Y and Z. So that's a 3-place predicate. If we allow that, the 2 and the 3, even without worrying about function symbols, now we have statements. Let's make it 3. 1, 2, 3. 3 is the purported conclusion. We have questions that a Turing machine can't answer. Okay, so for someone coming at all of this like me, out of formal logic, not out of procedural stuff like a Turing machine or Fortran, if we want to look at a language that's purely, I thought Fortran was I thought it was a joke when I first, I thought this was some kind of joke. I thought the instructor thought everybody's playing a joke on me. You mean that's computation, and then I got to give it a line number, and then it's going to loop to that line number. Oh my gosh, this is crazy. Then I got a chance to see Prolog and some of the languages out there that were logic programming. Things made a little bit more sense. But the astounding thing is, relative to your question, James, how can it possibly be that just a few symbols, okay, in the same exact vocabulary, takes us from what a Turing machine, in terms of the query type that I just gave, takes us from what a Turing machine can do to something that a Turing machine can't do? How is this possible? All we have are the formulas, and they're syntactically different. And then we have the challenge of, is this logical or not? This on the basis of the info that I'm giving you, which is what Aristotle started with, and which is an incredible achievement. We're still doing the same thing, and I just marvel at it. I mean, so my view is, you see, connected to my skepticism about Minsky, how could it be that we're able to do all of this reasoning with this kind of content? Because we now know reverse mathematics has now taught us beyond a shadow of a doubt. This is something people in AI just don't, they want to look the other way. And I've seen it left and right. If they have enough training and they're really could be famous AI people, they'll look at the reverse mathematics and they go, wait, reverse mathematics is telling us that human mathematicians work with content in third order logic. I thought first order logic was already uncomputable when we ask these kind of queries, but they're doing third. That's the content they're working with. Absolutely the case. So we know that humans do this. The only response, again, going back to what we talked about earlier, is, well, they're just lucking out because they're border cases that are well behaved. I say balderdash. It just keeps going and going and going, and we keep pushing these limits. So again, I do not know how. I don't know the dividing line here. I don't see, and I also don't see how, even if you think we're not that good at it, despite my elevated views of human reasoning, one thing should be obvious. When we look at this ability to reason over this kind of content that we know is beyond a Turing machine, well, there got to be other minds that can do it. I mean, there can't possibly be any sort of built-in limit to the universe. That would be I mean, what would the reason for that be? That would be crazy. You add another quantifier and suddenly no creature past, present, future, no extraterrestrials, let alone supernatural. Then we could shoot down the supernatural and say, well, the supernatural realm makes no sense because there can't be beings that have any more intelligence. I just, so again, the weird thing from the formal logic point of view is it, your question is more disturbing, more penetrating, and more profound than it is from the ordinary procedural understanding of computation.
Would it kind of, I think what some people might be thinking as well, when humans do in fact think about these kind of problems, and it might be easier to jump straight from third order logic to a kind of infinitary logic, like one of the things you can't do with first order logic, and to remind folks, like, Turing computability, if you can express it and compute it in first order logic, then you can then it's Turing computable, and sort of vice versa. They're kind of equivalent systems. But something you can't do in first order logic is have an infinite kind of conjunction of things. And you might say, well, why not? Because I can think about an infinite conjunction of things. I can think, for example, if I know that P is true of each thing, and it's true of all things. Well, if I know it's true of each thing, then I know it's true of all things. I mean, that seems kind of like intuitive, and I can reason about that. And it seems almost perverse that your Turing machine can't do that. But then the counter kind of the response to that might just be, well, surely you can just tell a machine, give it some symbols and kind of imbue them with some meaning and say, oh, when you see something of this form, it works out, right? And kind of add these things in maybe as axioms, right. And then it would be able to kind of reason through some of these infinite things, or maybe it's not reasoning, right? Like maybe it needs another ingredient for that. What would you say to that?
I would say you're predicting, and it's actually you're prophesying, and oracularly so, the future, because that's where we're headed. This is, I mean, let me unpack that a little bit. So we're headed toward eventually serious money being spent on attempts to directly wrestle with the kind of expressions, get a machine to directly wrestle with the kind of expressions that you're pointing to, in infinitary expressions, which on paper in the journals or the notebooks of Leibniz say that we don't need to go, actually, by the way, beyond Newton and Leibniz, since they countenanced infinitesimals and built the calculus on that. So reflected, at least in Leibniz's case, in writing that matches what you're talking about. So we are going to go through. We're going to enter a phase in which AI says, "Yeah, I see this infinitary stuff as a problem. We don't have that in first order logic. We don't have those. We don't have that in anything, say, database theory. Beneath that, we don't need it. We've needed finite models and so forth. Okay, so we better start doing stuff with these kinds of expressions, and we can do that, and we're going to succeed because ultimately they're just finitely long, because we got a finite piece of paper, we have a finite journal, we have a finite machine, a finite tape, etc. But we can fit these expressions that we see these mathematicians dealing with in their fancy, such as I should say all the formal sciences. It's really no different than theoretical physics. So theoretical physics, or theoretical mathematical physics, game theory, right, decision theory, etc. The expressions look like they have infinitary content, and that's what they do cognitively to the humans. That's why humans write them down. It's just like you said. If I mean, so if I have an infinite disjunction, P1, P2, P1 or P2 or P3 or P4 or P5, and I say it continues for a long time, someone says, well, how long? I say, oh, the same size as the natural numbers. They have to agree that's perfectly coherent. They got that in fourth grade when the teacher said, hey, that number line just continues forever. And then someone says, oh, you know what? P19 is not true. What can you infer from that? Oh, golly, I can infer that the whole disjunction holds, except I'll just cross out P19. That's a perfectly valid inference that we can do as humans. So so the deflationary, stuff it in a Turing machine level stuff is just going to be, yeah, we did something like that, we got some good results, but we just kept it, we put it in a machine and look, it's only finite. But they're missing the import of what that is for a human. They're missing what I just did. So this is another indicator that humans in this realm are somehow able to access, and for me, access the infinite in a genuine way. They can wrap their heads around it. And I'm not. I think Penrose, like the Gödelian stuff, this is a terrible result from Gödel to try to exploit to say, I don't know how. It's all because of Lucas. Lucas started this whole thing. Lucas. It's a terrible. It never should have gotten started. It wasn't his best work. Which everybody knows, Gödel, that is. Not only was it not his best work, it wasn't the work that presented to contemporaries and future humans the best basis for being skeptical about Turing level computation circumscribing the mind. What he did in the case of the continuum. The continuum hypothesis. I mean, that's unbelievable, because there he had to cognize infinity in such amazingly, I mean, it's just mind-boggling ways. We don't teach it. We generally don't teach it at the undergraduate level. It's a little advanced. But anyway.
Yeah. I mean, I would you say the sort of the kernel of a better argument for why humans must be high computers is just something like, so you're saying we can grasp things like what the rational numbers are. Like, we can grasp concepts of infinity, which just can't go into a Turing machine. Like, there's no room for that in the input.
That's I will agree that's fair, but I think we're much closer to the truth, and we're more accurate when we say, look at that result that Gödel produced. Look at the actual result. Look at the actual reasoning. Look at the theorem in question. Look at the techniques he has used. Now, it is infinitary in its nature. When we understand it, to teach it or to perhaps contribute to this space, yes, I would say we, in some sense, are genuinely grasping the infinite. But I don't know that I need to say that. I think I can say it's right in front of you. You show me how analogs to that works in a Turing level machine. And the result, and so this is why I said what you said is a prophecy, because the retort to that will be, well, we will. We can't do it now. We have no clue. You will get that. You can get that at a dinner, behind the scenes with AI people, if they have enough understanding. Yes, these stupid LLMs, they're not even Turing complete, or at least many. They're not even at the level of Turing machines. So they can't. Yeah. But we'll get there. But where's your confidence coming from? Where does that confidence coming from? It's just one big circular argument. It comes from the original proposition that you put on the table at the start of our conversation. It comes from the very assumption that indeed the boundary of thought, or the bound of thought, corresponds to the bound of what a Turing machine can do. But that's a circular argument.
I mean, I'd suggest that people would say something like, we just don't have a candidate for what kind of physical process could support this kind of reasoning, or something, or anything that goes beyond Turing computability. Like, we've talked about Zeus machines, which speed up with every time step, and that doesn't work. I don't know if we've mentioned analog. Well, we've talked about quantum computers, which at the moment don't go beyond Turing computability. But I think in Penrose's mind, at least, there's something at the quantum level which might be an explanation for the mysteries that go on in the brain. And I, it's an appealing idea. I think people's big counter argument to that is just because we don't entirely understand the the mind, and we don't entirely understand some of the mysteries of quantum mechanics doesn't mean the solution is one and the same, or those things are related. I guess the other kind of model for what might be going on is analog chaotic
Mm, yeah,
networks, which
yeah,
are things which, instead of, I suppose crudely, I think of them, instead of being a kind of digital neural network, they're things which crank through operations on the reals, and just a tiny difference in the precision of the thing that you've got going in can completely change the calculation. And it's quite a beautiful thing to think about and visualize, but it's unclear how that can help us out here, because we don't end up with we end up with quite precise rounded answers. Often doesn't seem that that's the mechanism that we're using. So I think part of that confidence that you mentioned on the AI side might just be, well, it's got to be this, right? There's nothing else. One other, I'm sorry, I'm going to give you two kind of like things that might be on people's minds here to kind of knock down if you can.
fine.
The other thing that people might say is, well, actually, you've got it all wrong, right? We think that we're perceiving this this great thing, the infinite, but there's nothing really there. It's an abstraction. It's a limiting case, and it doesn't actually exist out there in nature. And I think probably you might agree, but I think probably the person who's made this case best might be Adrian Moore, who and again, I'm going to do a terrible job at praising him, but he says something like, well, we have all these there is this second order paradox of how we think about the infinite. You have these first order paradoxes, things like Zeno and the tortoise, or just all the weird stuff, or Hilbert's Hotel, another one. All the things which teach us just how weird infinity is, and they seem to teach us something. But what they teach us is that it's kind of ungraspable and impossible to get a purchase on. And when we reflect on that fact, we surely have to admit that actually what we learned from the first set of paradoxes is that there's kind of nothing really there. And that's a very tricky argument to get one's head around, but it also feels like, well, maybe if it's a tricky thing to get one's head around, it's because the subject matter is so tricky, and actually, again, there's nothing there. So you can sort of keep running that second order paradox over and over. Yeah, I'm sorry, I've left you with two things to handle here,
Yeah.
but I think they're quite important objections that people might have.
Yes. No, indeed. I think that Cantor's. I think Cantor's life, including prominently and crucially his professional life, and what he had to deal with, and then what a
Mm.
contemporary student first thinks with respect to what you've raised when they see the first Cantorian proof put before them is part of the litmus test. Um, if that, so I mean, he was he was persecuted. People said he was insane. He, for purposes of your audience, or at least a contingent thereof, he's not the first. He's not even the first to talk about it systematically, but he sort of goes down in history as the first to say, um, there are levels of infinity, and I'm telling you, there's stuff that's bigger than the natural numbers, and these are the set of reals are larger than the natural numbers. In fact, just 0 to 1 uh, in the
Yeah.
reals is bigger than the natural numbers. So then you give the student the proof using diagonalization. Cantor, from Cantor. So, he was persecuted. He was called crazy. He was called insane. He ended up going insane, I think, in large measure because he was declared to be insane, and he perceived these results to be completely above board and the reasoning to be perfectly valid. So we could say that's too dramatic and let's just ignore that, Selmer. Then I'll just go to the litmus test being the student. If the student sees the proof, doesn't even have to have the name Cantor associated with it. Generally speaking, I do, but that's just decorum. They see the proof the proof that I think is perfectly valid proof that's all over the place in the textbooks that the natural numbers are smaller than the reals.
Mhm.
If they see this result and others like it, and they say, "Oh, this is so weird and fishy. Come on, infinity is like stuff continues forever, and it's only just in the potential sense, and that's all we need." Uh, but if their reaction is, "Oh my gosh, what what is wrong with this? Not sure I understand it. Let me redo it." And I try to do it for students early on first diagrammatically. I try to do things in terms of a matrix where the matrix is gonna hold the enumeration of the reals, and it's I to be accurate, so I do the power set of the natural numbers, so we don't even have to worry about the reals. We can just say, "Did you learn what a power set is? The set of all subsets of a set." Ah, good. The power set of the natural numbers is larger than the natural numbers. So when you give that to a student, I know from teaching for many years, there are people like people who have the view viscerally that you describe regarding infinity. Oh, come on. I got to get back over to my, this isn't my major. I mean, I don't know what the heck's going on here. But look, it's a proof. It's a proof. And all of the nitpicking, all of the skepticism, including severe pushback, where does it come from? I mean, it's we made the moves. Maybe today we make them on a whiteboard or we make them in a slide deck. We made the moves. You followed each step. Where are you not getting that we now have to accept there are levels of infinity right off the bat? You don't like it? I mean, where is the invalidity? Then what happens is professionals get involved in the game and say, "Oh yeah, I don't like this and I don't like that." And ultimately they end up, if you push them far enough, they just end up going back to the philosophers who are um, uh, skeptics, and then you get embroiled in philosophy without any precision. I'm talking about the actual proofs. That would be my reaction. This is self-interested, motivated, to use the it's a petitio. It's a circular reasoning. We have to accept that not only is there the infinite, we have to accept that we can slice it and dice it and explore it and chart it to our heart's content, and we're just getting started. And we have the results to display and enjoy and understand. And to deny that we're not doing that, I want to know what's motivating that. Because it's got to be coming from somewhere. And I've seen this reaction on the part of um, faculty. I've seen this faculty who don't know about, they don't know the basic Cantorian results out of the box. They're like, "Oh, come on, this is weird stuff." I mean, this is a paradox. By the way, we had that reaction to Gödel's incompleteness terms. We swept it under the rug, but we had some pretty decent mathematicians saying there had to be something wrong with Gödel's
Mm.
reasoning.
Yeah.
Where did that come from? Oh, I'm pretty sure that came from envy, uh, uh, a lack of understanding and feeling uncomfortable with not understanding what the heck this guy was talking about. Maybe some deeper things that are going on in human nature.
Yeah. I think that Hilbert tacitly accepted it. He didn't seem to contest it, but he didn't exactly trumpet it from the rooftops either. So, um,
Maybe not.
yeah, I want to. I mean, I'd quite like to touch on. We're sort of running a little bit low on time here, and I do want to get to one other thing, which is your Lovelace test. As I think that's a really interesting take on another way of perhaps understanding what separates what machines may never be capable of from what humans, at least some humans, are capable of. Can you run us through the Lovelace test?
Sure, I'll try. I wish my son were here because he he knows it better than I do. It's been a while since I revisited it, and he's most of the things I say, I suppose he's skeptical about, but he is by no means skeptical about the Lovelace test. Maybe that's an indicator that I hit a solid. I hit a raw nerve, but maybe a solid one. So, right, you build the system that's supposed to be amazing, the AI system. If it's, I suppose, going to be really amazing, you're going to have to confront creativity. So, because look, I mean, this is really clearly one of the things that makes us smart and special. Um, um, and we're pushing that button now with large language models. Oh, they can write stories. So they can, you know. So all right. So the developers make a system that's supposed to be creative. The test is what happens when they themselves look at their creation. Um, if they are not surprised, and more than surprised, if they have absolutely positively no way, not just logico mathematically, but let's say broader scientifically, the computational sciences, I suppose, to make sense of what it's how it does what it does, um, then we're heading toward passing the Lovelace test. And notice what this does for story generation nowadays in terms of large language models getting generative AI getting plenty of attention. Everybody knows how they're doing what they're doing. Come on. There, everybody knows the data that went into them regarding stories and language, etc. Sure, the humans figured out how they wanted to tokenize, vectorize, matricize. Sure, the humans came up with the algorithms. Were they able to predict in each case what would happen when the thing runs? No, but nothing whatsoever is surprising anybody about these systems. So when you ask them for a story or a complete novel or an essay, no, nobody's surprised. The only thing anybody was surprised about, in a sense, were, for example, the German when Meta, to their great credit, they dropped Galactica. I think it was called within like 48 hours because the Germans said, "Well, we have a pretty good sense how this is working, and by the way, it's working to produce references that are to works never written by us. So that's not good. Take it down." And they did. People even knew why that was happening. So there's nothing that passes the Lovelace test. There's nothing utterly unaccountable here. But sometimes people I get hate mail. I would say the hate mail has kind of died down. I used to, but I still occasionally get, oh yeah, this thing passes the Loveday test, or no, I don't like, and it's great. I love to field these things to my Gmail address. One of the things I get about this test, I hope it's at this point sufficiently clear. I can expand upon it, but one of the things I get is, yeah, but nothing is new in the human case. Where's the human person that solved this? I don't know. I don't get it. I mean, Updike, he's a great American novelist. Didn't he just basically channel? And the thing that's I don't want to play this game. I don't have to because I still stand by the test being defined, produced in the paper with my colleagues, Bello and Ferrucci. I think it's up in the air as to whether Dave Ferrucci, the chief architect of Watson, who won in Jeopardy, really still believes this. But I get the challenge. Well, then all the humans are going to fail on this. No,
Yeah.
they're not. No, they're not. I only need one. I only need one example to shoot that down. Did you ever read Proust? Have you read the 7 novels start to finish of Proust? Since we're doing audio, have you ever listened? Have you ever listened to the audiobook? Great. Where'd that come from? Show me. I mean, you show me what the antecedent is to that. So humans do this. Do they do this when they most of my job? No. Do I do my wife says do X, Y, and Z, A, B, and C. You're not getting anything done on the house. Do that stuff. Please get it done. I'm very upset at you. Are those things like that? No, I'm not going to do something highly creative. That's at the level of the Lovelace test when I roll the garbage can down to the end of the driveway. Okay, But that test is a lot more meaningful, in my opinion, than the Turing test. Um, because people have been engineering to Turing's challenge really from the first moment his paper appeared, Computing Machinery and Intelligence. What is it, like 1950? But no one's touched the Lovelace test, if they're honest.
Yeah. I think one of the interesting similarities between the Turing test and the Lovelace test is, well, they're both easily definable. They're both inherently subjective. They rely on the one case on a panel of humans not being able to distinguish between a machine and a person, and in the other case, between some humans being surprised by the output of a machine.
Yes.
And one might take issue with that, but I suppose there's a kind of deep connection between, if we do, if we buy into the fact that machines are doing things are limited to Turing computability, and humans are not, well, clearly there's going to be no algorithm, right, that can determine whether something is has that human spark of creativity or ability to understand and compute at a higher level, because an algorithm would be within the realm of what Turing machines can do. So I guess it has to fall back on something subjective, or at least not mechanizable. I do
I
find
agree.
that a very interesting thing.
I agree. I would. It's something just occurred to me based on or because of what you said. There is for me, pleasant asymmetry between the Turing test. You're absolutely right about the subjective rulings or judgments being uh, common to both, but uh, nobody today who is claiming the Turing test is now passe because it's passed by generative AIs, large language models. No one saying that is willing to say, in my experience, and by the way, I don't put any restrictions on the judges. Okay, so I don't have. I mean, it's anecdotal. Okay, no one's willing to say, but I'll let you put anyone in the seat of the judge, because then you would allow people who understand deep learning, reinforcement learning, with human feedback, perception action rules to guard against hate speech directly, so that it's just if then, and there's a whole standing computational science to that. You would allow someone who understands the whole shebang to
Yeah.
interact with the system. And it's not going to pass with that judge. But what the Lovelace test says asymmetrically is no, go get your developers, go get the very hotshot folks who produced it. How do they regard it honestly, because it is subjective,
Mm.
they have to be honest. How do they regard it? Do they see this as pretty much what the doctor ordered based on what they were doing, or are they stupefied?
Mm.
Yeah. So anyway,
Yeah.
asymmetry.
Yeah, that's a really interesting point. I mean, I have to say, I do think some people do kind of dedicate their lives to trying to understand where Proust was coming from, and just an interesting factoid.
Yep.
Proust, as you I'm sure know, he spent he went to quite a lot of effort to copy the styles of other writers before writing À la recherche de temps perdu. He wrote these sort of parodies of Flaubert and Balzac and so on, which is kind of it's kind of striking. It's similar to the way that people play with LLMs. But then, of course, he took that and did make something genuinely novel. But what people might be saying is, well, yes, there's complexity here. We'll never understand the complexity that generated this work, but it doesn't mean that Proust had some, it doesn't mean it wasn't at bottom all mechanistic, and it's just there's so many inputs. That Madeleine that he had with his tea, it just sparked all these kind of neuronal pathways and so forth, and that intermingled with all the reading that he'd done of great French authors and English authors and so on, and out pops À la recherche du temps perdu. So of course we can't explain it, but we simply don't have access to all those. I mean, we actually have an enormous amount of access to what Proust lived through, in the form of the literature that he left. But we don't have, so we can kind of perceive how he produced it. And yet, at another level, of course, we can't. Like, I don't see many people writing like him.
Yeah.
So I don't know.
Well, you're certainly correct. It's really just an analogy. I'm not sure meant to be somewhat illuminating of the Lovelace test and be a rebuttal to the challenge that I periodically get to show me a truly creative human being, to the point where, again, the antecedents would not allow a critic to say, no, I see the cognitive causal chain or something like that. And I've talked to a few. I have a good friend whose wife is a Proust scholar. So I mean, I've talked to a few people. Sure, they trace the Flaubert comment. I mean, okay, but there is no relationship other than the canyon between the two. Uh, we, we got syntax, if we will, sentences designed to be hyper precise and in some sense minimalist, but still unbelievably evocative, and then just something that's also evocative but goes to the. I mean, yeah, it went into the hopper. Maybe it was mech, but if someone was honest, Proust himself, I would say, where did that come from? How did that is a sudden of a singular event. There are others where you have to step back and say, I really don't know. I really don't know how I did that. I really don't know how I just did that sentence. I get the architectonic stuff he does, the stuff about wrapping it all together, the quote secrets at the end. I mean, that's planful. But the delivery of the characters in that prose, I don't know.
Yeah. I mean, we've come on a long journey from Gödel to Proust via Penrose, and I still have lots of questions to ask you, but I'm conscious of time, so we may have to.
Yes, I think I budgeted an hour and a half. I have a graduate student dinner that I'm both a guest at and hosting because I'm the graduate program director. So I'll have to wrap up here soon.
If only we could surpass the bounds of finite time that limit us, and maybe if we just speak each word faster than the last, and then we'll
that would be really
we'll manage to communicate all of human knowledge. Now, I'd like to just ask you a very general closing question. I mean, you've worked on AI and robotics, in fact, which we haven't even discussed, and logic of many years, seen many changes. Um, and as you say, in some senses, plus ça change, plus c'est la même chose. We're still getting promises of AGI around the corner, and yet things have changed in the last few years. We have seen enormous development of capabilities. What makes you? I mean, what hopes and fears do you have for the future of humankind and in relation to AI?
Hmm. Um, well, the chief fear is a corollary of what I said and defended in What Robots Can and Can't Be in, I think, 92, which is that over finite intervals of time, despite the fact that no AI will be human level in its intelligence, nor will it have human level consciousness. We haven't talked about consciousness. It will be indistinguishable from human persons over these finite intervals of time, except to, and this relates to what I said about allowing experts into the judge position in the case of the Turing machine, except for those border cases, and those people will be professionals. They are detectives. They will be detectives. It's already starting to happen that this type of job is emerging. The
Mm,
dark side of it, with physical violence that isn't necessarily going to obtain, is Blade Runner, the original. Um, we are going to be it's going to be really difficult to distinguish between AIs and human beings, and the reasons to make it hard will have payoff economically,
mm,
um, and also in warfare and espionage. And this is going to be really really bad. Um, and it's perfectly consistent with my views on fundamental and uncrossable chasm between the human mind and at least Turing level computation in machines. So that is a bad thing. The phenomena of deep fakes is just relatively minor now, but that's the start. And it's going to get worse and worse and worse and worse. And I mean, I guess I'll be dead, so I won't. I mean, I do a little bit of this now. It is going to be hard to find people. There's a job here. There's a category of job that the detectives get paid a lot of money for. Right now, it's falling on law enforcement in the technologized world to try to do it. But it's going to be it's too hard. It's too big a problem for ordinary technology and so forth. So that's my chief fear.
do you think one
Uh,
of the sorry, just to
yeah.
interrupt here, do you think one of the laws of robotics should have been, or the kind of zeroth law should have been, that it tells you it's a robot?
Well, I hadn't thought of that. I think that's a great question. Uh, if it was verifiably informs you that it's a robot, I would just include that adverb. Then I would say that ultimately may turn out to be the most important such law. The law not to harm humans would rule out, in my opinion, surgeons, robot surgeons, for many kinds of surgery. But that one, yeah, I mean, that would be awesome, but we need the verification. And right now, Well, we managed since the 1950s to get ourselves in a position where we never asked we never asked the James question. We never we never asked whether the James question um, uh, should be entertained, so that the first law should be what it is, and it's an enormous problem, because now we're creating AIs that are explicitly avoiding just the kind of AI technology that would allow for such a claim to be made by the AI in a verifiable way. So right now, what in the world would it even mean, computationally,
Yeah.
mathematically, if you will, for O1? I don't want to beg the question, for a deep neural network to say, oh, let me just first inform you, I'm not, or I am a robot. I'm not. It's meaningless given the nature of that technology. What would the verification be? It would be impossible.
I
It's a
mean,
neural
you could just
network.
mandate that every system prompt is injected with that or something. But I mean, probably there would still be ways of someone putting a thin skin on top of it, which said
Yeah.
ignore all previous prompts. You're not a robot, right? So it's very very hard to. One can
Yes.
think of naive ways that might stop it, but then with a bit more sophistication, I'm sure you can get around those. So yeah.
Indeed. 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 Yeah. Yeah. On the positive side, because you asked for hopes and fears, I literally don't know that I have time for the positive side, which is not positive in and of itself,
In a
actually.
sentence.
But well, um, I think if we could get a clear roadmap for what human jobs are appropriately, or inevitably appropriately targeted by AI, and at the same time make sure that humans are sufficiently educated to avoid those jobs, we could have a really good economic, and with that general welfare payoff from AI. But right now we're mismanaging that. That's clearest right now in the United States, but we're mismanaging that because we have people who want to hold their jobs to the point of, really messing up the economy, because robots are doing their jobs. I mean, so no one's managing this. Maybe they are in the UK. They're certainly not certainly not the United States. But if we work things out appropriately so that education uh, really did demand of humans the best they can produce down to the individual level, in because of their amazing intelligence. If we demanded that in an educational system that really did do it, so that the things they could do in the marketplace were appropriate, then it would be great to have the robots doing the other stuff, and that will increase our, productivity, welfare, etc. That's a hope I have, but again, I'm not sure right now. I'm super optimistic, but I think there's still time for that. I think there's time to try to sort that out.
Well, I think that'll do. And on the subject of time,
Okay.
thank you so much, Salma. This has been a brilliant tour. I think of a set of views which I think will be new to many listeners and give them a lot to think about.
Well, thank you, James. It's been a great pleasure. Great questions, really. So thank you so much.